Have you ever heard that a penny dropped from the top of the Empire State Building could be lethal because of how fast it would be going? It's a persistent myth that's been around for ages. But is there any truth to it, or is it just another urban legend? Let's break down the actual physics, and I promise you'll feel a lot better about walking near tall buildings. Here's the core idea, and it's super helpful. Imagine you're falling, not through air, but through super thick honey. The faster you try to move, the more that honey pushes back, right? Air acts kind of like that honey. It's called air resistance, and it's the hero of our story about the penny. Every falling object eventually hits a speed where this honey resistance perfectly cancels out gravity's pull. And when those forces balance out, boom, acceleration stops and the object just cruises at a steady speed. Okay, so let's get into understanding terminal velocity. When you drop something, two main forces are at play. Gravity is constantly trying to pull it down, that's a steady force. But then there's air resistance, pushing back up. And here's the crucial detail. Air resistance isn't constant. The faster an object moves, the stronger that air resistance becomes. It builds up, you see. So when you first drop the penny, its speed is tiny, almost zero. That means there's almost no air resistance, so gravity completely dominates, making the penny accelerate downward, picking up speed. But as the penny speeds up, the air pushes back harder and harder. Eventually, and this actually happens quite quickly, the upward push of air resistance becomes exactly equal to the downward pull of gravity. When these two forces perfectly balance, the net force on the penny becomes zero. And what happens when there's no net force? The penny stops accelerating. It just continues to fall at a steady, constant speed. That constant speed, that's its terminal velocity. Here's the mathematical relationship for how we calculate terminal velocity. Don't let the symbols overwhelm you. Let's break them down. V is our terminal velocity. Under the square root, m is the mass of our object, g is gravitational acceleration, rho is the air density, a is the object's cross-sectional area, and cd is the drag coefficient. What's important here is seeing how things like mass and shape, represented by a and cd, play a huge role, not just gravity. So why is a penny specifically such a poor killer? It comes down to a few key characteristics. First, it's super light, only about 2.5 grams. Second, a penny doesn't fall perfectly flat like a controlled disc. It tumbles, and when it tumbles, it presents a relatively large surface area to the air compared to its tiny weight. And third, that flat disc-like shape creates a lot of turbulent airflow around it, which really cranks up the drag. All these factors together mean a penny hits its terminal velocity surprisingly quickly and at a surprisingly low speed. If you plug all those values into the formula we just saw, a penny's terminal velocity works out to roughly 11 to 25 meters per second, which is about 25 to 56 miles per hour. Let's put that in perspective. That's closer to the speed of a really fast baseball pitch than it is to, say, a bullet. It's not a trivial speed, but it's far from the lethal missile people often imagine. It's more like being flicked by a fairly strong hand. This diagram visually walks us through what happens. The penny is released, gravity quickly overtakes air resistance, and it accelerates. As it speeds up, air resistance grows. This loop continues until air resistance perfectly matches gravity. At that point, the forces are equal, and the penny reaches its terminal velocity, settling into a constant speed of around 25 miles per hour. Then it just coasts harmlessly to the ground. Here's where most people's intuition actually trips them up. They think, oh, if it falls from a super tall building, it has more time to speed up, so it'll hit harder. And in a vacuum, you'd be absolutely right. Objects would just keep accelerating until impact. But we're not in a vacuum, are we? We're dealing with air. And air means air resistance. Here's the kicker. A penny actually reaches its terminal velocity after falling only about 50 feet. The Empire State Building is a colossal 1,250 feet tall. This means the penny spends almost its entire journey, over 1,200 feet, simply coasting at that constant terminal velocity, not accelerating. So you could stack 10 Empire State Buildings on top of each other, drop the penny from that insane height, and it would still hit the ground at the very same 25-ish miles per hour. The extra height just gives it more airtime, not more speed. Does that make sense? All right, Let's put our formula to the test and actually calculate the terminal velocity of a penny. We'll use some pretty standard real-world values for all the variables. You can see them listed on your screen. Things like the penny's mass, the density of the air, its cross-sectional area, and the drag coefficient for an object with its shape. We're also using the standard value for gravitational acceleration. Ready? Let's crunch these numbers. First, let's calculate the numerator of our equation, which is 2 times the mass times gravity. So that's 2 times 0.0025 kilograms for the penny's mass, multiplied by 9.8 meters per second squared for gravity. That works out to 0.049 kilogram meters per second squared. This represents the gravitational force acting on the penny, effectively multiplied by 2 for the formula's setup. Next up is the denominator, rho ACDP. This represents the air density times the cross-sectional area times the drag coefficient. So we multiply 1.225 kilograms per cubic meter for air density by 2.85 times 10 to the minus 4 square meters for the penny's area, then by 1.17 for the drag coefficient. And that gives us 4.08 times 10 to the minus 4 kilograms per meter. This value essentially quantifies how much air resistance the penny experiences for a given speed. Now we divide our numerator by our denominator, so 0.49 divided by 4.08 times 10 to the minus 4, which gives us about 120.1 square meters per second squared. And finally, we take the square root of that value to get our terminal velocity in meters per second. That's approximately 11.0 meters per second. We're almost there. To make that 11.0 meters per second more relatable, let's convert it to miles per hour by multiplying by 2.237. And voila, we get approximately 24.6 miles per hour. Quick check. Does that match your intuition now? A penny traveling at about 25 miles per hour isn't going to cause serious injury from such a light object. It's slower than most people ride a bike, and way slower than even a car in a residential zone, so the myth is busted. You're not going to get seriously hurt by a dropped penny. You've probably been hit harder by a playful snowball. You're safe. All right, let's recap the most important concepts from our lesson today. If you only remember a few things, make them these. First, terminal velocity happens when air resistance precisely balances gravity. For light, high-drag objects like pennies, this happens really quickly. Second, once terminal velocity is reached, extra height doesn't give you extra impact speed. The penny just falls at the same constant speed. Third, air resistance gets stronger with the square of velocity, which is why it creates a natural speed limit for all falling objects in the atmosphere. Fourth, the shape and surface area of an object matter even more than its sheer weight when it comes to terminal velocity. Flat, tumbling objects fall much slower than sleek, streamlined ones. Fifth, the penny myth sticks around because in our daily lives, we often intuitively think of objects falling in a vacuum, completely forgetting about air resistance. And finally, the terminal velocity for a penny is indeed only about 25 miles per hour, definitely not fast enough to cause serious harm. And most objects hit this within the first few seconds of falling, making building height mostly irrelevant for the final impact speed. Let's quickly clear up some common misconceptions that often trip people up. 1. The idea that higher drops always mean harder impacts. Nope. Once something hits terminal velocity, extra height doesn't increase that impact speed. 2. That pennies are heavy enough to be a real danger. With only 2.5 grams, it's far too light to sustain dangerous speeds. 3. The thought that objects just keep accelerating until they smash into the ground. That's true in space, but not here with all our lovely air. And 4. That the Empire State Building's immense height makes dropping a penny uniquely dangerous. Not at all, because the penny hits its maximum and relatively slow speed after just the first 50 feet of fall. The building is a whole lot taller than that. To really hammer this home, let's compare a penny's terminal velocity to a few other familiar objects. You can see how a tumbling penny at about 25 miles per hour is only marginally faster than a large raindrop, and its danger level is minimal. Now, compare that to a baseball which hits terminal velocity at around 95 miles per hour. That's a serious hazard, right? Or how about a bullet shot upwards which maintains a much higher speed because of its aerodynamic shape? This table clearly shows that even though it falls from very high up, a penny simply doesn't have the characteristics to be dangerous once air resistance kicks in. All right, your turn to practice. Why don't you try calculating the terminal velocity for a common quarter? I've given you all the necessary values on the screen. Follow the same step-by-step method we used for the penny. Calculate the numerator, then the denominator, divide them, and take the square root. Don't forget to convert your final answer from meters per second to miles per hour. Once you have your answer, compare it to the penny's terminal velocity and think about why they're different, even though they're both coins falling from the same height. You've got this. You'll find the quarter's terminal velocity is about 15.6 meters per second or 35 miles per hour, and you'll correctly be able to explain the difference. That's it. You've got this.